Hello my friends, let's talk about layers 1 and 2 of the OSI model today. And with that, looking at the center column, we're talking about the physical cabling that connects computers together, and at the next layer up, the data link layer, we're primarily concerned with Ethernet as a method for transferring data and packing it up into a series of ones and zeros in a way that computers can ingest them and use them. So starting off with layer 1, the physical layer, we're talking about the bits that are transferred from one device to another via a connection. And so that connection might be fiber optic cable, it might be copper, it might be sound waves. Unlike hard drive storage, where we're typically talking about bytes, when we're talking about data communications, we're typically talking about bits, which are oftentimes represented with a lowercase b for bits per second, megabits per second, gigabits per second, etc. And in terms of the properties of the media in this area, we are concerned with how fast that media can carry bits. So here are some of the names of the devices that carry bits at the level 1 physical layer, and then here are a few types of media at the end of this list. Again, the common media that we worked with tend to be copper, fiber optic, and radio frequencies. Over here on the right are some examples of our copper media. We have some of the coax cable, which is more like our original Ethernet way of connecting computers. And then we have the other three images being images of current cabling that we would call twisted pair. The one in the lower right is unshielded twisted pair. The one in the upper right is shielded twisted pair, and this is a terminated cable. It's a great media medium for transferring ones and zeros via changes in voltage to represent ones and zeros. The one on the right is shielded, and this is to protect it from electromagnetic interference, things like microwaves or neighboring devices. Anything that has electricity in it can potentially interfere with your cabling. And I've heard that this is more common in Europe as well as recently with Cat8 cabling and that sort of thing. But historically it hasn't been used as much because it's expensive and people don't think that the shielding really does a whole lot for us. In terms of problems with this type of medium, it has a limited range over which it can transfer information, and the longer a cable stretches, the more there is something called attenuation. Just means that the signal diminishes. So you throw something on there called a repeater in between long segments of cable to reboost the signal. Another issue we have is crosstalk, where one set of wires can have some of its ones and zeros jump over to another set of wires, and twisting is something that actually solves that problem for us, or it actually reduces it quite a bit, and so that's why it's twisted. And as we go into higher levels of twisted pair cabling that can carry more bandwidth, they tend to twist the cables even tighter. So here's a summary with a link to Wikipedia of different speeds associated with different categories of cable. So you can assume that if we come out with a Cat9 cable someday, maybe that'll be 100 gigabits or something per second. All right, here are fiber optic cables. We have glass or plastic that carries light and potentially changes in amplitude of those waves. Could be a way that would be a change of state. That could be a way of representing a 1 or a 0 as we pass light along one of these strands. There is a core, there is cladding around it. Two important types of cables we want to know about are single mode fibers. These are fibers that only carry a single beam of light. The advantage to these types of cables is they can carry information over much larger distances. Multi-mode fiber is a fiber that allows you to bounce light in different angles so that you can have multiple light streams or multiple channels carried at the same time. But it's not going to go as far as a single mode fiber will. So some of the, not that there's problems with it, it certainly goes a lot farther and faster than copper mediums, but some of the issues with it is that it can be brittle if you're bending it. You can break the glass inside. And also why it eventually stops transmitting information is there's this issue of dispersion where light particles will go off into the cladding and disappear. So you would need eventually some type of repeater if you wanted to have your cables going over a very long distance. Here's a representation of how sound waves and changes in pressure can be put into a wave, which could also be then used to transfer information, and a representation of a 1 and a 0. So you should take a moment to pause this video if you haven't already done this before as a group, and talk about what are the different types of media that I just talked about, how they communicate, and then consider how they transfer 1s and 0s. Okay, as part of our class, we made cables. Here's the instructions for that, and here is just so you know, there are actually different orders that you can put the wires in your twisted pair cabling, and this one is the B form of that, so it's not really important which order you put it in, just as long as it's consistent. Okay, so that gets us out of the physical layer. Now we're going to talk about layer 2, which is where we're actually concerned about what's in those series of bits. And in particular, we're thinking about a protocol called Ethernet, which basically says if we can get a long enough series of 1s and 0s, we can interpret it and understand what information is in there, such as ASCII information like letters, numbers, things like that. We can build those 1s and 0s up into something else. All right, so here's some concepts that we're going to want to know about network interface cards. Not so much about the media access control. That's a subset of the data link layer or layer 2. Really, there's a whole bunch of things this takes care of, but things like flow control and things like that. But we don't really need to talk about that for our course. MAC addresses and Ethernet protocol. So 3 of those things we need to know a lot about. Here's a little image off to the right where we're looking at the OSI layers and then the data units that are transferred within them. So starting off with a network interface card. A network interface card is something that can read 1s and 0s from the physical medium that it is attached to. So that could be a copper cable, or it could be a wireless signal. Something about these to know is that every single one of these devices has a unique MAC address associated with it, media access control address. So these are assigned by the vendors. The first 3 digits of the media access control are associated, well, I wouldn't say digits, but the first 3 pairs of digits, the first 3 bytes technically, are associated with the manufacturer of the device or that card, and the last 3 are the unique identifier. So again, the first 3 bytes or 24 bits represent what the organization is that built it, so it could be Apple or Intel or 3Com, and then the last 24 bits help us, or 3 bytes help us distinguish one card from another if they were made from the same organization. So let me show you how we can work with this. I'm going to create a little spacing here and type in clear, and then I'm going to type in ifconfig. If you are using a Windows computer, you would type in ipconfig space /all, and it's going to show you a listing of your connections to networks. And what I'm looking for on this particular one is EN0, which means Ethernet 0, and then it has these numbers right here. So technically, these correspond to what we're seeing right there. But it's written in hexadecimal, so technically those first 2 characters represent 8 bits. The next one represents 8 bits. So each character actually represents 4 bits, so half of a byte. So on my particular device, the organizational identifier here is 8C8590. So that would correspond to Apple being my manufacturer. And then these last 3 digits, among all the other MacBook Pros that are out there, this is going to be a unique sequence of numbers, which I could translate into 1s and 0s with not too hard of math, to be honest, with each of these characters representing 4 bits. If I were to pull up my Windows computer, give it a second to start back up again, I will be able to do something equivalent. I can do the ipconfig /all, and I apologize for a little wait as this comes up. Okay, so if I were to type in ipconfig /all, you can't quite see everything here, but let's kind of, right here it says it thinks that my physical address is 8C8590, etc. Okay. Also, if it's of interest to you, you could go out to a website and Google the organizational identifiers for MAC addresses, and you would get a site something like this one, which comes up with just thousands and thousands and thousands of, well, it seems like that many anyway, because I'm just scrolling forever on this page, the prefixes that represent a particular manufacturer. So this has implications for security and debugging issues. If you can see the MAC address of the device it's connecting to you, you can know more about which type of device it is potentially. Okay, so that's that. So what I just showed you was an individual MAC address, and so this is mine that I had. There are some other MAC addresses that you might see if you're sniffing the traffic on your network. I'll jump to the last one first. A broadcast address of FFFFFFF, etc. That's all ones if you're looking at it in a packet sniffer like Wireshark. This is an address which, when a switch or something like that sees it, it's going to broadcast the message out to everybody in the network. So when people are trying to find, like if a particular device is trying to find out who has a particular IP address within a network because it wants to communicate with that IP address on a local area network, it'll send this message with this destination address rather than an individual address so that everybody in the network hears it and has a chance to respond. Multicast is an important technology when, for example, we're streaming information and a whole bunch of computers need to subscribe to it. So imagine the situation where you're broadcasting a movie or something like General Conference and millions of people need to see it. Well, do you want to have millions of individual streams being sent to every individual computer that's subscribing to it, or would you rather have it so that there's one stream coming into an individual network, and then if 100 or 1,000 people want that, then it gets just reproduced over all the ports in the switch that are there. Well, multicast ranges allow us to do that. We can subscribe as a particular network card to a range that we're listening to if we're simultaneously listening to the same stream. So that way we can have one stream coming in and it can be duplicated not at the source but just at the last hop right before it connects to our cards. So that's I use that to send gigabytes of information to every computer in the lab and things like that. Okay, now on to another fun topic. So we've talked about how we have a medium, and we've talked about how we have addresses associated with those mediums. Now let's start talking about how we send information. And we might think about information in terms of a letter. A letter has a from and a to and a payload, meaning the things that's contained inside. So let's take that analogy and associate it with the actual words that we use in data communications. So one of the things that we talk about are datagrams, which are something that has a header, meaning we know where it's going, and a payload, meaning some important information to deliver, so that would be the letter inside of an envelope. And then we have different types of datagrams depending on the layer of the OSI model that we're talking about. So if I go back to this one, if we're talking about the physical layer, we're talking in terms of bits. If we're at the data link layer where we're talking about Ethernet, we tend to be talking about frames. And it's just a set of ones and zeros, oftentimes up to 1,500 bits. The network layer, we could call that a packet. And at the transport layer, when we get to that, we call that a segment. It's all just, some 1,500 to 2,500 series of bits. But when we're talking about it at different layers, we use a different name sometimes. Sometimes a packet is good enough for all of them, but specifically we use a frame or a packet or a segment when we're talking about particular layers. All right, so with that, it makes sense that as part of any of our packets, frames, or segments, that we know where the packet originated and where it's going and what it contains. Where it's going. All right, and so one of the most important protocols we have and collection of technologies that we have at the layer 2 is Ethernet. And Ethernet is, a little over 1,500 packets or bits on the high end. So we could, another way of talking about, sorry, not bits, I should say bytes. So a byte is 8 ones and zeros. And an alternative word we have for a byte is an octet. And that's just a fancy way of saying we know that this byte contains all ones and zeros. I know, it's kind of a weird thing, but whatever. So we have basically in excess of 1,530 to 40 octets or bytes that are associated with an Ethernet packet or frame. When we're talking about it at the layer 1 level, where it's just the ones and the zeros without meaning, we might talk about that as a packet, but we're really more concerned with it at the next level up, which is an Ethernet frame at layer 2. So it's called a frame at this layer. And if we look at the contents of it, we have 6 octets that have our MAC destination. Hey, we just saw MAC addresses. We have 6 octets that represent the source. So it's where it's going to, where it's from. We can ignore this other stuff. And then the payload, that's the message. And then maybe some check at the end of it. Here's another way of representing that. Although this is not an Ethernet 2 frame, it's when I'm analyzing packets, I don't see it listed this way, but it has the same idea. So here's just a shorter way of having our Ethernet 2 frame. Again, MAC address. Here's an example of it. That's the destination. This is the source. And then a little bit more information, the data, and then a checksum that we could use to determine the quality of the information that was sent. So maybe we could see this. So let's analyze this in Wireshark. So I brought up Wireshark on my computer. Maybe I'll resize this window a little bit so that we can see it better when I do a capture. Okay, if you'll be patient for just 1 second. Because of the spark line, I can see which network interface device is picking up traffic right now. So there's my Wi-Fi. I click on it. It's picking up some packets. And because there's always communication going to and from me all the time, not too bad right now, I'm going to hit stop. And I want to look at one of these packets, this one that says it's a type TCP packet. I have a source IP address and a destination IP address. Let me jump down here. And in this second window, we have a frame. So a frame is the thing that's the bits on the physical layer. But then here's our Ethernet 2 frame. And if I expand this out, as I highlighted, it shows me the corresponding information here that's associated with that. And I can go back and forth from hexadecimal to bits. If I expand this out, what's of interest to me that relates to what we've just learned is I can see a destination address. So it's showing me that I'm going to 0024C3. And the way I'm reading it kind of indicate on the left here, it's kind of already parsed out that it knows that this is a Cisco manufactured device. And then the last 3 things, 3 octets are associated with the unique address of that device among all the other Cisco devices. This next one down here, as you recall, this is my address that I showed you before on a previous slide. So that's the source. So I'm sending something from me to somewhere else. And these first 3 octets or bytes are associated with my address as a Mac computer. And anyway, we could mess with the hexadecimal, and we could very quickly see how an 8 is associated with, in this first block of blue, 1000. We'll cover that on another day as we convert binary to other numbers. All right, so now that we've seen that, let us talk about some of the underlying principles for Ethernet. Ethernet uses something called carrier sense multiple access collision detection. If you envision in your mind the original coaxial cables that look like your TV cables, everybody was sharing it in a bus format, which means that everybody's seeing what's on that one cable at the exact same time. Everybody's connected to it. And so multiple access, that means everybody's connected to it. And then collision detection, this means that if two different computers start to talk at the same time, it can notice this as a computer, as part of the Ethernet suite of technology, say, hey, two computers tried to communicate one of these things that we just talked about, which is a frame, which might be up to 1,500 bytes long. Two computers, if they start to try to send 1,500 bytes at the same time, the computers that are both sending at the same time can detect that there's a collision. So a collision is a big thing in the old technologies. It's not a big deal now because with our switches we tend to eliminate they're not sharing really the same cable all the time. Our switch kind of filters out the communications. But the underlying technology is still there as part of Ethernet, that they could have a collision. And what happens is if two devices talk at the same time, sending their up to 1,500 bytes, think about it in the terms of like a telephone conversation where some people start going, no, you go first. So same kind of thing happens here. If two computers start talking at the same time, they recognize that they both were talking at the same time, so they will both stop talking, and then they will wait a random amount of time and try to talk again. So they do have something called collisions where they theoretically can talk at the same time under Ethernet, and then they'll back off and wait random amounts of time and then start trying to talk again. To me, it's kind of a miracle that this stuff even works, because you'd think that computers would collide all the time. But then when you're talking about only 1,500 bytes and the fact that you can send millions of bits per second, I might have said bytes a minute ago, I meant to say bits, but the fact that you are only sending, well, I guess that is true. Sorry, that is accurate. I am talking about bytes. Anyway, the fact that you're talking, sending 1,500 bytes or so potentially at a time, and that you can have millions of bits being transmitted per second, even in the older technologies, that leaves plenty of space to send along small packets and work around one another and take turns. But it's still kind of amazing. Okay, that's really the last thing that I wanted to talk about, but you might take some time to read through these slides to just get some further clarity and definition about what the Ethernet protocol does, how a repeater can help forward on communication, this idea of collisions that we just talked about. This introduces this term collision domain. So some of our networking devices then eliminate the possibility of having two devices talk at once. So sometimes we'll say and collide with one another. So when we talk about that, we're talking about a collision domain. And one of the functions, I mentioned another in class, but one of the functions of a bridge as we separate networks is they get rid of the collision domains so that computers on one part of the network can't collide with another. Technically, a switch is called a multi-port bridge. It just makes it so that it's almost like every single computer plugged in when you plug it into a switch is really shielded from the possibility of doing collisions. But read through those things and you will know what you need to know for this portion of the class.